Hello everyone. We'll be reviewing the activities of the GSC in the Thompson Valley Corridor today, with a particular emphasis on preliminary results of new UAV surveys and a differential InSAR analysis of RadarSat constellation mission time series from last year. The National Railway Network crosses a physiographically diverse continent susceptible to a broad range of landslides. A key mandate for NRCan and Transport Canada is to protect national socio-economic infrastructure, like the railways, the environment, natural resources, and public safety. To this end, our work provides fundamental geoscience and evaluation of technologies for understanding and monitoring landslides across the country. 3 rail corridors traverse the mountains and plateaus of southwestern British Columbia, with railway infrastructure, other transportation modes and communities along their way at risk from extremely rapid avalanches, rockfalls and debris flows, through to slow-moving rotational slumps and translational slides. Today's presentation will focus on activities at Ripley, Nipper and South Slides, 3 landslides of concern along the Thompson Valley Railway Corridor, with a long history of sporadic climate-driven activity. Throughout the talk, you'll see the first outputs from a collaboration between the GSC, Transport Canada, Innovation Solutions Canada, and Spexy Geospatial Incorporated. Using Spexy's remote piloted aircraft system platform and an RTK Phantom 4, we have captured and processed orthophotomosaics, digital surface models, and digital elevation models for 5 of the landslides of concern in the vicinity of the Black Canyon. It took only 2 days in October and November of 2021 to acquire these baseline datasets for future UAV change detection monitoring and benchmarking of InSAR and RTK datasets. Beginning with Ripley landslide, we have captured the state of the surface following BGC's site investigations in 2019, or was it 2020? Here you see the distribution of GCPs around the slide and field evidence that the slide is still active. Although the smallest of the monitored landslides, we've established Ripley has a representative internal composition and failure mechanism, with shallow rotational translational sliding of clay-rich glacial valley fill, driven in part by spring melt recharge through tension cracks across the slide main body, changes in water levels across the toe slope, and hydraulic connections across the shear surface, daylighting in scour pools. I'll briefly mention the brief success with our GeoCube network. Before it closed down for the winter, we captured renewed activity across the main slide body, with up to 4 centimeters of displacement recorded between March and September of this year. Again, deer have been the bane of this installation, contributing to the system failure in early October. Following reports of renewed displacement captured by a BGC inclinometer at Nipper Slide, we established a dense network of ground control points across the slide body and around the stable perimeter. We flew the slide with Spexy in October using the RTK Phantom 4. Although a much larger feature, the stratigraphy and failure mechanisms are proposed to be similar to Ripley. We'll be looking at Nipper more in years to come. Now on to the most active landslide in the Thompson Corridor, the North Slide Solar Slump. Last year we reported on a short RCM time series indicating parts of the toe slope in proximity to the CP mainline were deforming at rates of 2.5 centimeters every 4 days. This is equivalent to almost 2 meters a year. This result demonstrated RCM's capability to capture landslide movement, but required further benchmarking. In September 2019, we installed 13 ground control points across the solar slump and on the active floodplain of Thompson River. Resurveyed in September 2020, the 3 ground control points closest to the riverbank showed annual displacement amounts of greater than 3 centimeters. Corresponding to zones of greatest displacement captured by RCM InSAR, RTK GNSS captures 16 to 20 centimeters of northwest displacement over the year. This movement is interpreted as a surface expression of rotational slide blocks failing along shallow shear surfaces in clay-rich glacial lake sediments that extend under the river. This year, we began a more sophisticated comparison of geospatial datasets at the solar slump. Point cloud analysis of UAV datasets reveal a spatial footprint of deformation corresponding very closely to the RCM results. RCM westward line of sight displacement values from January to September are clearly underestimates when benchmarked with RTK GNSS measurements indicating 10 centimeters of northward displacement from March to September. Displacement vectors were generated using M3C2 point cloud processing of UAV datasets acquired in September 2020 and September 2021. These show the solar slump failing to the northwest or west-northwest as the Thompson River erodes and unloads the slide toe. Before closing, I'd like to briefly outline some other potential applications for a scalable RPAS. Beginning this year, Transport Canada and NRCan began to explore new linkages and applications for UAVs and SPEXI's RPAS platform. An example is illustrated here, showing provisional results from an infrastructure evaluation test in eastern Canada. UAV overflights on a via rail track near Smiths Falls, undertaken at the same time as the Thompson Valley surveys were conducted, aimed to capture baseline photogrammetric data to assess the quality of ballast, ties, and trackside drainage. To close, I'd like to present a conceptual best practices model for understanding landslide form and function, based on our experiences in long-term monitoring of landslides in the Thompson Valley. 3 levels of investigation build upon each other. First, fieldwork, lab analysis, and remote sensing technologies contribute to a foundational knowledge on landslide composition and recognition of geoindicators of slope instability, for example, soil moisture, groundwater, and river levels. Second, benchmark UAV, InSAR, RTK, GNSS, and other datasets, for example, prime electrical resistivity tomography, capture baseline conditions and rates of change across monitored landslides. Third, the goal of long-term monitoring with a suite of remote sensing and in-situ tools is to derive thresholds for triggers of landslide activity. Our progress in the Thompson Valley and hopefully post-COVID, the Assiniboine Valley, will be confirmation that landslide monitoring and targeted maintenance are effective alternatives to costly mitigation solutions. Before I go, I'd like to acknowledge the assistance, guidance, and financial support from the stakeholders and contractors mentioned in the slide. This R&D is a collaborative effort, and its success is a reflection of everyone's contributions. Thanks, and I look forward to a productive 2022 and beyond.